Hello, Chem 20. So out of all this lessons that we looked at, the last three lessons, the first two are kind of review. This one is where we start to get into new stuff and some of our essential stuff. So we're actually going to break this apart a little bit as well. We are looking at pages 21 to 28, which is a lot, I know, so bear with me here. Page 21 to 24 inclusively, so 21 to 24 including 21 and 24, is going to be enrichment, which means we might have a really quick look at it just in case you ever run into it again. You won't be like totally lost, but you don't necessarily need to spend a ton of time on it. If you want to, if you're bored, go for it, but otherwise don't worry about it too much. And then page 25 to 28 is going to be our essential for this one. And I'm even going to do this. If you do page 28, that's great. Page 28 is a bit of a challenge. The only reason it is a bit of a challenge is because it involves more unit conversions, but yeah, we can do that. So let's jump right into it. We are talking about concentrations, and we mentioned before that concentration is always the ratio of solute over solution. So if we think back as to what that means, solute is the thing that is being dissolved, and the solution is typically the entire thing. Sometimes the entire thing includes both the solution, or sorry, the solute and the solvent. Sometimes the solution we just consider to be the solvent if it's the main thing that's there anyways. And we'll have a look at how that works, but it typically always comes down to that ratio, solute over solution. Cool. So the first little bit that we're talking about, again, this is enrichment that we're talking about on this first page, this page 21 that we're looking at right here. And I should also mention, if you don't already have it, have your workbook open to page 21. Your data booklets, probably your periodic table for this one is good for your data booklet. And of course, you will need a calculator to follow along with. So, communicating these concentration ratios. There's actually three ways that we're going to look at, 3.5 ways that we'll look at today. Again, the last, page 25 to 28, by the long shot, the most important. Cool. So the first way is via percentage. This is about as hard as calculating percentage on a test, right? So you know how to calculate percentage on a test. It's what you got divided by the total number on the test and then times 100. Check out our formula for this. This is for all different types of percentage concentration. Percentage concentration is equal to the quantity of solute divided by the quantity of solvent times 100. Perfect. So that's not too bad. And actually, we could even change this a little bit here. Let's make that a little bit more accurate. Quantity of solution. So what part of the overall total solution? I've never really noticed that typo before. So there's a couple different ones that we have here. There is percent volume by volume. That's typically when we have a volume, so a liquid in a liquid is a really big one that we look at with that. There is also percentage mass by mass, so percentage by mass or percentage mass by mass. That's typically a lot of times when we have a solid divided by solid, so the mass of one solid divided by the total mass of the solution. And then there's mass by volume or weight by volume. So if we look at all these, they're kind of the same. We've got the solute divided by the solution, the solute divided by the solution, and the solute divided by the solution. All we're really doing is switching the units for those. So if I wanted to get in this really quickly, vinegar. When you buy vinegar at the store, if you had a 5% acetic acid solution and we had 100 milliliters of that acetic acid solution, so 100 milliliters, what this really means is that 5 milliliters or 5% of it is HCH3COO, so that's our actual acetic acid part. The other part of it is, so 95% of it, or 95 milliliters, is just water. right? So 5% acetic acid, that's what it means. Out of the total 100%, 5% is the acetic acid, so the hydrogen acetate, and 95% is the water. Isopropyl alcohol, so this is something that you might buy in the store, the stuff that you put on a cut if you get scraped or something like that. It's 70% volume by volume. What that again means is if I had 100 milliliters of this solution, 70 milliliters of it would be our isopropyl alcohol. So that's C3H, I believe it's H8, OH. Shoot, we might want to check that one. Doesn't really matter for this one, to be honest. But you might want to check it. I think it might actually be C3H7OH. But we're just picking at straws, as long as we get the ideas. And then the other 30 milliliters would, of course, be water, so our liquid water. Cool. So that's about as much detail as I'm going to get into it. The only other thing that I'll say is in our formula up here, let's highlight it in blue. So in our formula up here, you should be able to, if you're looking at this extension, you should be able to rearrange this formula and solve for any part. So the most common one is typically solving for the percent concentration. But if I ask you for the quantity of solute, could you rearrange and solve for quantity of solute? Or quantity of solution, could you figure that one out? So that's sort of the scoop there. Let's skip ahead. Let's look at, let's see, we're on page 22 here. Parts per million concentration, and that kind of leads us into parts per billion. Typically you find this when there's very, very, very small concentrations, very small concentrations. So the amount of oxygen dissolved in a lake, the amount of mercury found in fish samples or something like that. So very, very, very small. It's very similar to percent concentration, except it's so small. If we put it in percentage, it'd be like 0.0000003%. So rather than do that, we say parts per million. So how many parts solute per 1 million? Make sure I got the right amount of zeros here. So there's 100,000. There's a million per 1 million parts solution, right? And it's got to be pretty small if you have like 5 parts per million. So 5 parts of your solution are whatever, say, a toxin is, and then the other million essentially parts are your actual solution that make up your entire solution. So when we look at our formulas for this, it is pretty dang similar, and I typically like to stick with this one. Typically like to stick with parts per billion for this one, because it looks an awful lot like that percentage, right? So concentration in parts per million is the mass of the solute divided by the mass of solution. Notice the units are both grams here, so grams over grams. And then instead of trying to get it into percentage form, multiplying it by 100, we actually multiply it by 10 to the power of 6. You might already think to yourself, oh, 10 to the power of 6, that's a million. Absolutely, we're getting it into millions, parts per million. Parts per billion, if we see down below here, parts per billion is the exact same thing, except we're doing 10 to the power of 9, right? So that's even smaller, even smaller, way, 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 way smaller. Another way that you could think about this is 1 part per million is 1 milligram in 1 kilogram of solution. That's a huge difference. A milligram is tiny, whereas a kilogram is fairly sizable. So again, this one is our enrichment learning. If you want to check this out, if you want to look further, absolutely go for it. Again, you should be able to, if you're checking out their enrichment, you should be able to deal with the calculations and kind of figure out what my solution is, what my solute is, and then be able to go through and check it out. Check out our Google Classroom for a little bit of help there. I know that the detailed answer key is on Google Classroom that you can check out, and if you're focusing on that, I bet you'll have no problem. So that's a bit of extra problems. Okay, here we go. Here is our essential learning. So if we have quizzes or tests or anything, this is what will be on essential. When you move into Chem 30, you will absolutely need to know how to do this. So molar concentration, also sometimes known as molarity, and often with chemists just called concentration, because this is the one that we always keep coming back to. So molar concentration, molarity, or just concentration. So when we talk about molar concentration, we actually have a little formula for this. We're going to try and not use the formula as much as possible. We want to look back at some of those things we did in review, like unit conversions are going to be a lot more powerful for us. So molar concentration is equal to the moles of solute divided by the moles of solution. And for us, that's honestly going to be how much water we dissolve it in, because the volume of the solution doesn't really change that much when we dissolve compounds in it, right? So the volume of solution is just the volume of water that we're dealing with. Cool. And that leads us to a little formula. C is equal to N over V. One of the things that you may have noticed in our data booklet from Science 10 to Chem 20 is that we don't actually get any formulas, or at least very, very, very few formulas in our data booklet. So all formulas that we have, we need to memorize. And that is kind of why we are looking at conversion factors instead of memorizing formulas, because conversion factors are just a skill. You don't need to memorize a skill, you need to practice a skill. And once you practice that skill, just like any other skill, you've got it. Absolutely, you've got it. Whereas things that you're memorizing, right? Memorizing's a little bit tougher. Memorizing stuff comes, stuff goes. And also there's a ton of stuff you got to memorize if you're doing that. Okay. So a little bit of review here. We kind of talked about this in our review lessons. So if you haven't watched those, you might want to, but you'll at least want to read through this. So remember, amount is the number of moles in chemistry. Mass is the mass, obviously, measured in grams. Molar masses are the conversion factors that we're going to use between mass and moles. So molar masses are kind of important. And then our concentration is our conversion factor. So concentration measured in moles per liter is actually going to be our conversion factor for going between liters and moles. So we'll use a combination of conversion factors this time around. What do you notice about conversion factors? So molar mass is grams per mole. Concentration is moles per liter. There's always two units, right? One on the top, one on the bottom. So something to look at there. So another thing that's kind of important for us before we jump into examples is the way that we write concentration. So writing the word concentration all the time is kind of annoying. So what chemists do is they actually, rather than writing the concentration of ammonia, the concentration of hydrogen ions, is they use square brackets to represent. So that H plus aqueous in square brackets means the concentration of hydrogen ions. The NH3 aqueous in square bracket means the concentration of ammonia. So that's a little shortcut. We will be using that quite a bit here. So make sure that you're familiar with that little shortcut. So the examples here, I'll kind of walk you through these ones. These ones are, the first couple are already done for us, but that's okay. We can still use them, we can still look at them, and we can still learn from them. And then there's a couple on the next page that we'll walk through, and then there's lots of practice for you to try out for this. So question number 1, determine the concentration. So the question is asking us to figure out the concentration when we have 1.2 moles of sodium hydroxide in 450 milliliters of water. First and foremost, 450 milliliters of water, if we want moles per liter, we probably just kind of want to ditch that, right? And we want to put that in liters, so 0.450 liters. Cool. Now, even though we're taking 1.2 moles and that has some volume, and 450 milliliters, that's obviously a volume as well, the actual solution is just going to be 450 milliliters worth, which is kind of neat, right? It's the moles of sodium hydroxide. The sodium hydroxide fits between the water molecules, and it doesn't actually change the volume, which is kind of crazy. So if we are using, let's see, where's some space over here? If we're using our formula for this, we'd say C is equal to N over V. Cool. C is equal to N over V. We'd plug the number of moles in, 1.2 moles divided by the number of liters, 0.45 liters, and we'd end up with over here 0.67 moles per liter. So not bad. We can use a formula, but again, that kind of relies on memorizing a formula. The thing that we really want to do is really focus on those units. right? And that's how we start to use this unit conversion. And this one's a little bit tricky just because there's no conversion factor in this one. But when I'm looking for the concentration, I don't know why I drew that arrow like that. Let's fix that. When I'm looking for the concentration, I am looking for moles over liters. So I'm going to start with one of the two things. I'm going to write out 1.20 moles of sodium hydroxide. In this case, because it's all sodium hydroxide, you don't necessarily need to write out NaOH. I'm going to start with 1.20 moles. Cool. And then my other number, 450 milliliters, or 0.540 liters, I'm sort of treating this as my conversion factor, kinda as my conversion factor. I know that I need to end up with moles on the top and liters on the bottom. So I currently have moles on the top. That's a good thing to start with. And I want to end up with liters in the bottom. So liters just has to go on the bottom here. And I know it's 1 just as a placeholder rather than as anything with an actual unit. 1 over 0.450 liters. And then when I plug that into my calculator, it's probably not turned on. There we go. I'm going to do 1.2 divided by 0.45. Oops, 0.45. There we go. And it works out to be 2.6666666667 moles per liter. And you might be thinking, well, why is it 2.67? Remember that review video? Significant digits. So from my original question, I've got 3 sig digs and also 3 sig digs from that volume. So my answer should have 3 sig digs, 2.67 moles per liter. So that one's a bit of a funky one. Absolutely, it's a bit of a weird one. Let's check out one that I think we'll see that conversion factor a little bit more. So determine the concentration is the question. So determine the concentration. We are looking for the concentration of sodium chloride. If we got, okay, 25 grams of sodium chloride into 650 milliliters. So let's see, 25 grams, that's a mass. And you know what? I might even erase that top question just to clean things up a little bit here. There we go. You can always rewind. That's the beauty of this if you're missing out on that one. So let's see, back to the pencil. So I got 25 grams, that's my mass. My volume is equal to 650 milliliters. Again, we kind of want that in liters, so 0.650 liters of water. Perfect. So determine the concentration, that's my question. I'm understanding the concentration is in moles per liter. So what do I need to find? I need to find the moles, and I need to divide that by the liters. So that's not too bad. That's not too bad at all. If you remember our conversion factor going between mass, because we're given mass, 25 grams, and moles, you might remember that it is indeed molar mass. So the molar mass of sodium chloride, when you add up the molar mass of 1 sodium plus 1 chlorine, works out to be 58.44 grams per mole. So here's what I'm going to do. I'm going to actually cross out question 3. You do not cross out question 3 because we're going to do it in a second, but I'm just going to use this for a bit of extra space down below, and then I'll erase it. You still need to do question 3. Please don't cross it out, especially not with pen. So we could go through and we could say, oh, well, mass is equal to, or sorry, amount is equal to mass divided by molar mass. So that's going to be, let's see, 25 grams for every 50, or divided by 58.44 grams per mole. We see our units canceling. We'd end up with however many moles of the substance. I don't actually know, so I'm going to plug it in. 25 divided by 58.44. So apparently that's 0.4277, 0.4277, I'm going to round it off at 9 moles. Cool. So this is again using memorized formulas. We just kind of plug in there. Now that I've got the moles, I can go through and I can say, oh, well, C is equal to N over V. I know that my concentration is the moles divided by the volume. So that's 0.4277 moles divided by my volume, which was 0.650 liters. Okay, not so bad, not so bad. Where'd that calculator go? Actually, the answer should be right up top there anyways. So I'm just going to take this, I'm going to hit divided by. We'll see answer divided by 0.650. Apparently that's 0.6581. Let's go back to the original question and look at significant digits. So let's see, I've got 3 sig digs, and I've got, oh yeah, 3 sig digs. So my answer should definitely have 3. Where'd that go? 0.658 moles per liter. So perfect. There's our answer using formulas. We still need that molar mass for a conversion factor. But yeah, kind of simple when we use this. What I really would like people to start looking at is not using formulas, but just using conversion factors. So when I look at the example up here and I check out the example and I see what they've done, they've started with 25 grams. They've started with the solid, the one number that they're given. They know that they need to change that into moles. So just like we practiced before, we say, okay, well, if grams is on the top here, I needed to cancel with grams on the bottom in my conversion factor. So things on the top cancel with things on the bottom. Cool. So if I were to pause right here, so just kind of forget about this piece and all the answer and use my conversion factor, I would have moles of sodium chloride. That is the exact same thing that we did down below here. We said 25 divided by 58.44, but we got that intermediate answer. But we're not done yet, right? We're not done. So now I've got moles. And now I want to say, okay, well, I don't really want moles. I want moles per liter. So I've got that 650 or milliliters or 0.650 liters. I need moles over liters. I need the liters. It's red for some reason still. I need the liters to go. I have no idea what color this is going to be. The liters to go on the bottom so that my answer is in moles per liter, so moles over liters, which is cool. So if I were to plug this one in, I'd go through and I'd just do 25 divided by 58 point, what is it, 44, and then divided by 0.650, and I end up with the exact same thing. The exact same thing. So for now, whether you're using sort of the idea of formulas or using conversion factors, honestly, it doesn't matter too much because we've only got 2 formulas. Realistically, we should start to lean more and more and more towards conversion factors. They're going to be a much more powerful tool. Okay, what is going on here? Why do I have a... Oh, because it's 3 and it somehow got separated on the PowerPoint. I hope it's not quite as ugly on yours. Sorry about that if it is. I tried to go through and check everything. But also, I must have deleted B at some point. So let me just clean this one up, and we will have a look at number 3. And then we will have a look at number 4. And then it's time for you to practice. I don't know why I'm doing this the slow way. Okay, go back to this, and whatever color we have is good enough. And then we just need to know, what are we actually looking for? 1.24 moles per liter. Come on. There we go. A 1.24 mole per liter solution. So I'm just rewriting this so it's all on one page. So determine the volume. So volume is our question mark of sodium sulfate solution produced if we've got 35 grams of the solute preparing a 1.24 mole per liter solution. Cool. So the goal of the question is to determine the volume. Volume is a question mark. We know that the mass is 35 grams. We know that the concentration is 1.24 moles per liter. Let's see, we know that it's sodium sulfate as well, right? So what is sodium sulfate? Na2SO4. And now that we know the formula for Na2SO4, we could probably go ahead and figure out the molar mass of sodium sulfate. So sodium, when you look at it on your data booklet, and please do look at it in your data booklet, 22.99 grams per mole. but we've got 2 of them, so I'm going to multiply that by 2. I've got one sulfur. I better check sulfur. I think it's 32.07. It is, so find sulfur and see the 32.07. We got 1 of those, so I'm going to add to that 32.07. And then we've got 4 oxygens, so I'm going to do 16 times 4. So the total mass of the entire thing, 142.05. Molar mass is equal to 142.05. And of course, that will be grams per mole. So let's just think this one through, right? And we'll use our conversion factors to help us out. We are looking for the volume. So volume's got to be equal to this whole big thing. Cool. So I don't really have enough information to use. I'm going to use a red pen to kind of highlight here, to use my conversion factor moles per liter yet. We're going to need it because that's the only place we really see liters, but I don't have moles yet. So maybe we should try and find moles so that we can use our moles to figure out the liters. Hopefully that makes sense for people. So let's see. I know that I've got 35 grams, and I always like to start with a thing that can only really be written one way, either do or do not have 35 grams. There's no 2 units in that. Again, you can put that over 1 if that makes your life a little bit easier, having a distinctive top and a very distinct bottom. Then I'm going to use my molar mass as a conversion factor. So my molar mass, it's grams and moles. I'm not even worried about the number yet. I'm worried about the grams and the moles. So I want to cancel out grams and end up with moles. So grams needs to go on the bottom. Things on the bottom cancel with things on the top, and moles need to go on the top. I know that it is 142.05 grams for every 1 mole. So the 142 has to go with the grams, and the 1 has to go with the moles. This is awesome because now I've got the number of moles. Perfect. That's the only unit I have left is the number of moles. So I might want 1 more conversion factor here to give me liters. Awesome. So I have in my concentration now, I've got moles and liters. So I want to get rid of moles, so I'm going to put it on the bottom. Moles on the top, cancel with moles on the bottom. I want to end up with liters, so liters has to go on the top. Now I know it is 1.24 moles for every 1 liter. Awesome. This is great, right? What's the only unit that's left in this entire formula? Just liters. And what are we looking for? We're looking for volume, just liters. Nice. Okay, so if I wanted to plug this in, I do 35 divided by 142.05. And then let's see, divided by 1.24. So my answer should be 0.1987, and we've got, let's see, 3 sig digs, so 0.199 liters. Cool, very, very cool. Very nice. Notice we didn't plug any, let's get that calculator back up over here. We didn't plug any of the ones in, right? And we just said, okay, it's 35 divided by 142 divided by 1.42. Because remember, anything on the top, we just keep multiplying. Anything on the bottom, we just keep dividing. So if I were to do this, I could say 35 times, oh, even before that, 35 divided by 1 doesn't change anything, times 1 still doesn't change anything, divided by 142.05, that definitely changes something, times 1 doesn't change anything, and then divided by 1.24 definitely changes something. Going to give me the exact same answer. So multiplying by 1, dividing by 1 doesn't really change much. Cool. If I wanted to look at this, and just for the sake of, okay, let's go back to this one, seeing what we're looking at here, we could use the formulas for this as well. So I could use N is equal to mass divided by molar mass. So I know the mass, I know the molar mass, we could definitely solve for N. And then I could use C is equal to N divided by V. Now I need to rearrange this one a little bit. So let's see, V's on the bottom, so I better move that to the top. The only way to move things is to work in opposite operations. So I'm going to multiply both sides by V. We see V cancel, and then let's see, V times C, I got to move C, working in opposites. I divide one side by C, I divide the other side by C. Cool. So then V is equal to N divided by C. That's essentially what we did in the formula up top, right? I would argue that up top, while it's a little bit more confusing to start, is probably a lot easier in the long run, right, than memorizing and dealing with formulas. But anyways, check this out. If you need to go back and pause, that's cool. There's lots of other YouTube videos out there that'll help you out with this. I know this is 1 or 2 examples that we're dealing with, but this unit conversion stuff, this is the bee's knees. This is good stuff that we're looking at right here. Cool. One last example. Determine the mass, so that's our question mark, of ammonium sulfide. We'll probably have to figure out what that is. Required to prepare 1.4 liters, that's my volume, of a 0.450 mole per liter solution. That sounds like my concentration. So as we go through, again, things that I got, I really like making a variable list. So we're given the volume, 1.4 liters, and we are looking for the mass. The mass is my question mark. I know the concentration, that's 0.45 moles per liter. That's a little messy. I do need the molar mass of this one though. So ammonium sulfide, geez, we'd better think about that one. Ammonium is NH4 and it's got a charge of +1, and sulfide is S and it's got a charge of 2 negative. So I think we're going to need 2 ammoniums for every 1 sulfide. So I can figure out the molar mass, no problem. Absolutely, we can do this. So let's see. We have got 2 nitrogens. So that's 2 times the molar mass of nitrogen, 14.01. Cool. Everybody, I hope, can find the molar mass of a single nitrogen. We've got 2 of them. Plus, we've got 8 hydrogens in total there. 4 times 2 is 8 hydrogens, so 8 times 1.01. And then plus, we've got 1 sulfur, 32.07 is the molar mass of 1 sulfur. So that works out to be, where'd it go? 68.17 grams per mole. Now I should mention, if you're confused about this molar mass stuff, go check out the review video that includes molar mass. Go check that one out. So anyways, as I go through and I check this out, I'm looking for mass. My conversion factor between mass and moles is molar mass, so I'm definitely going to need to use that at some point, but I don't have the moles yet. So I should probably use the conversion factor between liters, which I do have, and moles, which is concentration, moles per liter. Perfect. So those two kind of go together. Let's go back to the original felt pen that we had here. Yep, that's the one. So I'm going to start with 1.4 liters. Nice. I'm going to use the conversion factor that has liters in it to try and find moles. Cool. So again, if you want to put that over 1, that's no problem. So let's see. Liters is on the top. I'm starting with it on the top. I need to put it on the bottom if I want to cancel. Always the same thing over and over. And then moles, I want to end up with moles, so moles has to go on top. So liters cancels out with liters. Awesome. Then I just look over here. It is 0.45 moles for every 1 liter. Hey, does that 0 at the end really matter? I mean, it does for significant digits, but is your calculator going to care? Not so much. Your calculator says 0.45 is the same thing as 0.450. I say it's not, but your calculator doesn't care. Cool. So now I've got moles. Now I've got enough information to go from moles and molar mass into mass. So we can now connect those two. So I need to use my molar mass. Molar mass has grams per mole or moles per gram. Doesn't really matter which one goes on top. It's the conversion factor between. In this particular case, though, I want to get rid of moles. So moles has to go on the bottom, and I want to end up with grams. So grams has to go on top. So moles on top cancels with moles on bottom. The only thing that we have left now is grams, which is absolutely perfect for mass. Absolutely perfect. So let's see. It was 68.17 grams for every 1 mole. 68.17 grams for every 1 mole. Fantastic. I think all we have to do now is plug some numbers in. So let's just put this off to the side over here. It is 1.4 liters times 0.45 moles per liter times 68.17 grams for every 1 mole. Nice. And that works out to be 42.9471 grams. Let's see, back to the original question up here. I'll highlight this in green. We've got 3 sig digs and we've got 3 sig digs again. So we really want to make sure that our answer has the correct number of sig digs. So that's going to be 42.9 grams. Now, one thing that you might notice from this is that your answers for big section as this are now in brackets after the question. So your answer is here. Your answer is here. That's not part of the question. That is your answer. Cool. So answers in brackets afterwards. So could you go through, and I guess this is sort of the question here, could you also think about this in terms of the formula? Let's just go through and check this out, knowing that our goal is part of the formula. I'm going to cross this off. You please don't cross this off. You're going to have to do this one. But knowing the formula, I'd use C is equal to N over V to solve for N. So N is equal to C times V. Cool. Then once I have N is equal to mass divided by molar mass. And I'd rearrange and solve for mass. So mass is equal to amount, or N, times molar mass, which is pretty much what we just did, right? So we're given one either volume or mass, and we use a conversion factor to figure out the moles, and then we use that moles and another conversion factor to solve for whatever we're looking for. Cool, so that's essentially all there is to it. I'm gonna erase this, and I'm just gonna remind people right at the end of the video here, this is all essential stuff that we just talked about. We spent so much time talking about molar concentration or molarity, or often just known as concentration. Page 25 to 28, and then I'm going to say 28 equals challenge. It just has more conversion factors in it, or like milligrams and kilograms and millimoles and stuff like that. So it's just a bit more of a challenge. But you should definitely be able to do page 26 plus 27. So anyways, I'll leave you there. Try it out. Let me know how it's going. Please stay in contact with me. And yeah, bye for now, Chem 20s.